So if you have a 50 megawatt turbine and you have to take it down for maintenance, you have no power. If you have 50 megawatts of linear generators, the probability that you have 48 megawatts at any one time is extremely high because you can service units individually and have the rest of them continue to operate.
The amount of hydrogen that's produced in the United States today isn't even enough to power a 500 megawatt facility. So, we have a long way to go before hydrogen can displace a material amount of the fuel consumed.
Yeah, and that's one of the first impressions people have when they hear 250 kilowatts. They think, oh, that's too small to be a grid scale asset. But one of the things that's really unique about the technology is that we achieved high efficiency and low emissions that are better than a 100 megawatt gas turbine.
Welcome back to the Interchange Recharged. Utilities are facing a challenge where they need generation that's dispatchable, affordable, and clean enough to meet environmental requirements, which are three things that are notoriously hard to achieve together. And today, we're exploring a technology that most listeners probably haven't heard of, which are linear generators. They promise fuel flexibility, fast dispatchability, and near-zero local emissions. I'm joined by Shannon Miller, CEO of Mainspring Energy, who manufactures linear generators, and Will Hazelip of National Grid Ventures, whose team is deploying the first commercial hydrogen-powered linear generator on Long Island in New York. Shannon and Will, welcome to the show.
Thanks. It's great to be here.
Yeah, thank you for having us.
Shannon, I think it's best to just start with the basics here on what is a linear generator, how does it work, and for listeners that are familiar with other distributed generation technologies, how do you distinguish linear generators from engines, turbines, or fuel cells?
Absolutely. We started working on the technology by recognizing the advances in power electronics to replace mechanical systems. So we use the power electronics that are used in solar inverters, batteries, and EVs to redesign the generator from the ground up. And that allowed us to replace those mechanical systems with electrical systems and software. And that gives you something that's a lot more reliable, a lot lower cost, a lot simpler, and a lot more flexible. And so that sort of fundamental basis is what allows us to then have the features and the attributes that linear generators have. So they're more modular, more scalable, very high efficiency, very low emissions, and very fuel flexible.
So ultimately, a linear generator, it's not doing any kind of combustion, though, like we would see in a coal plant or gas plant, right?
That's right. There's no combustion. We still use the energy in the chemical bonds of the fuel to create electricity. So there's still a chemical reaction, but it's at much lower temperatures and there's no flame. And what that means is that we don't produce the NOx emissions that you typically see from an engine or turbine.
Okay, I think that gives us basics. I'm sure we'll go into more of the details and the advantages later as we talk about the Long Island project. But Will, maybe I can get over to you and give you a chance to talk about this project that you all are deploying and get into the specifics. Can you walk us through what it is that you're building? What's the capacity? Where does it sit within existing National Grid infrastructure? And what's the timeline for the linear generator deployment?
Yeah, happy to. Maybe just to start with what National Grid's role is in the energy system on Long Island. We own about 65% of the electric generating capacity on Long Island, so power plants that are extremely important for keeping the lights on, the air conditioning going in the summer. And for us, this is a really, really important step to test some new technology that Shannon just talked about. In an area that's a non-attainment zone, nitrous oxide emissions are extremely important. And we're really excited to be able to partner with the state of New York through NYSERDA, the New York State Energy Research and Development Authority, as well as the Long Island Power Authority, who's the local electric distribution company, in Stony Brook University, to deploy this linear generator at one of our power plants on Long Island. So having all that infrastructure really made it possible for us to pick a great site to be able to deploy this first linear generator. So it'll be 250 kilowatts. So it's one of the units, which I'm sure we'll hear more about. And we're going to run this for a year using both hydrogen as well as compressed natural gas. But as Shannon said, the fuel flexibility is really interesting, as well as the low emissions. So very low nitrous oxide emissions from a unit like this. So we think it could be a really, really valuable and critical generation technology to deploy in places like Long Island.
And what's the timeline for it becoming operational? Where are you both in the collaboration process?
Yeah, we're in the late stages of the development process and plan to have this unit running in the fall, in about September, and then we'll run it for a year in this program to do a lot of testing and see how things go, and give us a good sense of what we can do more with it in the future.
And so I think this is the first commercial hydrogen-powered linear generator, what a mouthful, that I've heard of at least. And it seems like National Grid is kind of taking a first mover position here from a utility standpoint. You mentioned the non-attainment zone, emissions being pretty critical, hence why linear generators have an advantage here. But Will, could you maybe walk me through the decision process? What are the challenges, or what challenge or need were you trying to address on Long Island, and what were you evaluating that made linear generators running on hydrogen the right choice for this project?
Sure, yeah. So, I mean, we've been working on this for a number of years, and it's really anchored in the way that the energy system is changing and evolving. So this isn't just New York, but New York certainly, we see a very significant transition underway, adding more and more renewables to the electric system. And the power plants that we have today will run less and less, but they will still be needed. Some sort of dispatchable energy source will still be needed to run when renewables aren't available. So in New York, that's called a dispatchable emissions-free resource to get to the endpoint of a carbon-free or net zero power grid. And so we were really looking for viable ways to deploy a dispatchable emissions-free resource, and hydrogen is a great fuel to be able to do that. Some really good qualities. You can make hydrogen with renewable electricity, and then when you use it in a generator, it doesn't produce CO2. And so to us, we thought, well, that's that's all the characteristics of a dispatchable emissions-free resource you want. And as we looked around at what kind of technologies are out there, that could do this, the linear generator really stood out for several reasons: the efficiency, but also the fuel flexibility. Because the big challenge at the end of the day is the hydrogen supply. So clearly we can get some amount of hydrogen today, but that will have to ramp up in the future. So having that flexibility allows you to deploy generators like these, the linear generators, that can run on the fuels that are available today, but then switch and run on hydrogen in the future.
Thanks for sharing that. And I think the fuel flexibility, along with the near zero NOx emissions, are of the two key points that we've touched on so far. Shannon, we've mentioned this a couple of times. Can you walk me through the emissions profile of your equipment, how it's able to work with so many different fuels and offer this kind of really unique advantage compared to other pieces of equipment for the energy transition?
Sure. The fundamentals really go back again to the design of the technology and the fact that we're using software to control how the system operates. So we use something called an adaptive pressure cycle, which allows us to adjust how we're operating in real time to different fuels. And that's what allows us both to switch between different fuels, but then also to control the reaction to get rid of the flame and the high temperatures, which is what creates the NOx emissions. So it's really that software enablement that helps us achieve both of those goals.
Do you find that it's typical for your other customers to have this kind of dual fuel or maybe tri-fuel mindset where you're experimenting with hydrogen and CNG? Is it of the utmost importance to your customer to kind of have this fuel flexibility? Is that often why they choose your technology?
Yeah, the flexibility is a really key driver for many of our customers. Many customers care about the sustainability opportunities where they can switch to cleaner fuels over time or lower carbon. But it also really supports reliability by having multiple fuels on site and you have a fuel supply problem, you can switch to a different fuel. So we have customers that are running with propane backup so that if the natural gas gets diverted for heating in the winter, they've got the opportunity to use another fuel that's on site. And we have a number of biogas customers where the quality of the fuel is changing over time, and that fuel flexibility really supports quality changes in the fuel as well.
For the Long Island project, Will, you mentioned that there's hydrogen that's being used as well as compressed natural gas. Is that green hydrogen? And would you be able to speak to where that's coming from or the logistics of how that's being transported to the site?
Yeah, certainly. Happy to do that. Yes, it is. It will be green hydrogen. We've contracted with a company called Certarus, who will supply the hydrogen in tube trailers. So trailers with a bunch of tubes on them, full of the compressed hydrogen. And it'll come from several different locations and be trucked in. And so we'll bring one truck in each month, and that'll plug right into the linear generator. And then we'll also be able to switch that out with compressed natural gas. So same sort of setup there. So again, a trailer with the compressed natural gas, and we'll be able to just switch them back and forth in real time.
How does the linear generator site, fit in with your existing infrastructure? Is there a future after this testing period in which it could be a regular hookup?
Yeah, certainly, whether it's at the site. So this project is at our Northport power generation facility. It's the largest power plant on Long Island, over 1,500 megawatts, traditional steam powered generation. And we'll be able to install this at the site and essentially plug it into a load bank. So we'll be able to run the linear generator as frequently as we want for as long as we want. And that power will be used at the site, and we could continue to use this in that application after that initial 1 year period. But we're also thinking about other areas around our system that we may want to deploy that and take advantage of different fuel opportunities as well.
You mentioned that this is a 12-month testing period. So what is it that you're trying to learn or test out? What defines success for this year-long period?
So Stony Brook University is part of this, and they have a number of different things they want to look at and measure. We know the technology works with hydrogen, so we'll be looking at the fuel switching and then just generally getting more familiar with this type of technology so that we can think about where are all the different places we could deploy this in the future. So for us, it's more about getting the experience with it. Stony Brook will be, looking at emissions and measuring efficiencies. And then for the state, for New York, I think it's a lot about seeing how this technology works and the emissions benefits that they come with it, so that they can think about how to manage it from a regulatory process perspective in the future.
But Will, you had mentioned hydrogen and compressed natural gas being used in the linear generator. Is it going to be cycled between hydrogen and compressed natural gas? Is it going to be blended? Are you going to try both?
I think right now the plan is to do one then the other. But we can change throughout the course of the program, and if we think there's some value in testing that blending application, we'll certainly do that.
And Shannon, it's totally capable of blended hydrogen, compressed natural gas. There's no issues with hydrogen embrittlement, leakages, anything like that.
No, we're happy to support blends or running individual fuels, and I think it really depends on the customer and what their needs are.
And so, Shannon, is this Mainspring's first deployment with a utility?
No. We have other deployments with utilities, but like you said, the first one with hydrogen and utility, and we see this as a big step to be working with NGV on this.
What have you learned from the other linear generators then that you have in the field, whether it be with the utility or other customers? What kind of performance data and operational results have you gathered over the past couple of years to prove your technology?
Yes, we started with commercial and industrial applications where we were powering logistics centers, cold storage applications, and doing a lot of EV charging. And so we learned a lot in those applications, just in terms of how to integrate with a site, how to integrate with solar, chargers, batteries, the rest of the infrastructure that is required to make the power systems work. And now we're starting to move into data centers, utility projects. So we have a number of larger projects now that we're doing where we're starting to dispatch into the markets with utilities and provide 24/7 power for data centers. And so in each of those applications, there's things that we learn, and we've had fantastic customers that are helping support our scale.
And through the conversations that you've been having with larger scale projects that I can imagine you're talking to with data centers, this unit is, Will mentioned, it's a 250 kilowatt unit. It's one of the linear generators that you have. Can you maybe talk us through the scale and the modularity of a linear generator? What's is the size of a single unit 250 kilowatts, and then what does scaling up to a utility or data center scale look like? If I need several hundred megawatts, what's the footprint look like? What does the economics look like?
Yeah, and that's one of the first impressions people have when they hear 250 kilowatts. They think, oh, that's too small to be a grid scale asset. But one of the things that's really unique about the technology is that we achieved high efficiency and low emissions that are better than a 100 megawatt gas turbine. And so what that means is that we can use that smaller scale device to work and support all sorts of different applications, everything from a logistics center to a larger grid scale application. And because the efficiency and emissions are better, typically that isn't true with engines and turbines. And so they have to use the bigger asset when they have those bigger applications. But because we can achieve those same, better performance at smaller scale, we can really go after that full market range and have a tool that can be used across that full power spectrum. And the benefit of that is that you could right size the project. So you can build it modularly and scale it to be whatever the utility needs. And, we'll know this. I don't know how, I'm sure it's very hard to anticipate what load growth is going to look like 10 years from now. And what our technology allows utilities to do is solve for today's needs and not necessarily have to anticipate what's going to happen 15 years from now. And you can right size the installation to be today's use, not overextend the costs, and then continue to build out as needed.
And it also has that fuel flexibility aspect that you mentioned. Is there any limitation with the load factor, the ramping up capabilities of the linear generator to?
No, and in fact, that's one of the other benefits is because of the small size, we can actually hold efficiency over the entire range. If you've got 100 megawatts, and we can still hit the peak efficiency even down at 125 kilowatts, that means that over the entire range of operation, we're operating at that peak efficiency, whereas a turbine or an engine is going to typically show lower efficiencies at lower load. And so having that modularity improves the performance. The other thing it helps is with reliability. So if you have a 50 megawatt turbine and you have to take it down for maintenance, you have no power. If you have 50 megawatts of linear generators, the probability that you have 48 megawatts at any one time is extremely high because you can service units individually and have the rest of them continue to operate.
Will, I know I asked that question, but I heard you starting to say something. Would you like to pitch in and compliment?
Is that last point that Shannon brought up, just the reliability benefit of having a fleet. So we think about that when you think about very large energy systems, or say Long Island. You look at the entire fleet, and some units will be down sometimes, but the fleet average is what you depend on for reliability. So it's like the microcosm of that in each power plant deployment, where you have these modular units. The other another important benefit, especially in this day and age with volatile supply chains, is an ability to have a unit that's essentially built and delivered in a fairly easy install. So really the amount of work we're doing at the site is primarily a concrete pad. And then this unit will come in and be placed on that pad, and then we'll do the electrical hookups and then the fuel hookups for the trailer system. That's a lot different than a 2, 3, 4 year construction cycle where you have lots of different components coming from lots of different places around the world, and potentially having shipping challenges or any number of challenges in that supply chain. That's a big benefit to just have one unit, and really all you're doing is pouring some concrete.
I'm hearing all good. It's a lot of pros here. I guess my question would then be, what's it going to take for utilities in the U.S. to start putting these containerized linear generators all over?
Shannon can speak to it, but I think they're having a lot of success. Seeing a lot of uptake. So certainly need to see more production. More megawatts being produced each year to be deployed. And I think it's there's a lot of opportunity, whether it's a utility or a specific customer. There's a lot of applications that this really fits the bill.
Shannon, just from your perspective on the manufacturing front, what is the manufacturing capacity that you have today and that you hope to build out to meet that eventual demand?
Yeah, our current facility, our current factory can produce about 325 megawatts a year, and we're the benefit of the design. The hard part was the design, not the manufacturing, and so we can add that capacity fairly quickly, 12 to 15 months, doubling that capacity. So scaling to a gigawatt fairly quickly over the next few years. And I think the biggest challenge for Mainspring is really just visibility and having people be aware of the solution. So that's our goal is to really just help people understand the value proposition of the product and where it can help.
Well, maybe we can talk more about the fuel flexibility aspect of the technology and how that might change the economics, because it's quite unique to linear generators. I can say from the WoodMac research perspective, we're looking at new build hydrogen capable turbines in North America, for which there's really not any, but we estimate capital costs to be very high, $3,500 to $4,000 per kilowatt, and the delivered electricity costs potentially reaching up to the several hundreds, $300 to $900 per megawatt hour, depending on the utilization. And this is largely driven by hydrogen fuel costs, not really the turbine cost. And if linear generators can run on hydrogen, but then also switch to compressed natural gas or biogas, blended fuels, how does that change the economic picture compared to being locked into one fuel?
I think that's exactly the value proposition, because fuel costs can vary. And so the ability to use the lowest cost and the most available fuel means that you're not left with a stranded asset that can only run on one type of fuel. And so I think that's exactly the value proposition that our customers are looking at, and like that flexibility.
Yeah, and over time, as carbon markets develop, it gives you that ability to make the trade-offs in real time. Assuming you have the fuel available, the costs, then you would make the decisions to say run on hydrogen if the carbon value is high, and then be able to switch to natural gas. So that's purely from an economic standpoint. Obviously, there's a lot of policy considerations that can come into play as well. But from an asset optimization perspective, being able to switch in real time just creates that much more efficiency as you're optimizing the asset.
As I mentioned, some of the costs from the turbine perspective, they're extremely high. You mentioned some policy support. Maybe the investment tax credit can help lower some of the cost of the linear generator, perhaps. But is the advantage of linear generators compared to, let's say, a hydrogen-capable turbine, is it primarily in the capital cost, or is it mostly in the fuel optionality aspect or operational efficiency?
I'd say the main benefits compared to a turbine, really the lower NOx emissions. If you run hydrogen on a turbine, the NOx emissions tend to actually get higher because the temperatures go higher. And so having the low NOx and the higher efficiency, the more expensive your fuel costs, the more important efficiency is, because
Mhm.
you're using less fuel to make the same amount of power in a higher efficiency device. So the real benefits are higher efficiency, lower emissions, and then the fact that you don't have to change the hardware out between the systems. So um, that's really the main drivers.
Yeah, and I think as you think about how this develops, again, the constraint is hydrogen supply, and so that will uh, grow over time, but the rate at which that growth occurs would be very important. So if you're going to build, say, a 250 megawatt um, power generation facility, and you do that in one turbine, that's hydrogen capable, but the hydrogen supply, it takes 10 years to get that hydrogen supply, then maybe you've overbuilt. Whereas with the linear generator and the modularity and ability to switch back and forth, you have a lot more flexibility to match the size and the use of the hydrogen as the hydrogen becomes more and more available. So we just see it as a more flexible fit in a lot of ways for a lot of applications.
I want to get to the point about market dynamics, hydrogen availability, but I have one more question about the operational aspect, which is, given that the fuel costs are such a dominant factor, whether it be hydrogen or gas, where does a linear generator make the most sense economically? Is it baseload generation, running constantly? Is it peaking applications, or somewhere in between?
We're actually doing both with different customers. And that sort of, again, leads back to the flexibility, because it depends so much on the fuel costs, the fuel availability, and then the nature of the grid that we're integrating with. If there's a lot of renewables, then we may be more of a dispatchable asset that is ramping up and down to support very low cost solar and wind. If we're in a location that doesn't have those assets, we may be running more baseload, where the alternative is another gas facility that's lower efficiency. So I think really just depends on where we're operating and how we're operating, and that's we have customers too where they start with us running baseload because they don't have access to more power from the grid, but they plan to shift to use us for demand charge management and peak load shaving after they get more grid access.
And I guess, Will, you're the perfect example. How is it that you're planning to operate the Long Island facility? Will it be baseload, respond to peaks, or operate flexibly based on grid conditions or fuel economics, or just the testing that you plan to do over the next year?
Yeah, the testing will be very specific to achieve the desired outcomes for that program. Beyond that, it really depends on where in the system we would put an asset like this, or this asset. If it's in a load pocket, then we would look at that specific application and expect it to run more base load, and then we would be doing that because that's a better alternative than a conventional turbine or engine type of approach. But in general, we would look at in a broad kind of energy system, we would look at this as more of a mid-merit type of asset. So running about half the time, not necessarily all base load. But there are a lot of considerations there as well. So if you're designing from the ground up and have all the space and all the fuel and et cetera, you may very well choose this as a baseload application because of a lot of the benefits that we've discussed. But in a more traditional application, especially where you're space constrained, you may still look at baseload coming from a turbine. The other thing that we'd be thinking about is how that evolves over time. So back to the renewable penetration is important, because baseload will change over time. The more renewables are added to an energy system, the less and less the non-renewable generation is going to run. So if that's going to happen within, say, 5 years, then you don't need to build a big baseload gas turbine. it might not make sense to do that. The
Hmm.
efficiency gain, the difference in heat rate won't necessarily pay for itself. So it just comes down to, to the specific economics of the application, and then how that energy system is going to evolve.
You mentioned, and I'm not sure if you're able to share, but the specific outcomes of the program, meaning the Long Island project. What are the desired outcomes for the program?
Yeah, it's really, I think we're looking at three different sets depending on, on the participant. So for us, we're really looking to get experience with this type of technology, how it works, the operation, the even doing the project hazard analysis for hydrogen. So you were already
Hmm.
developing quite a bit of knowledge around how we would deploy this in other settings. Stony Brook is going to be measuring, the emissions, the efficiency, a lot of the technical details. And again, I think, NYSERDA from the state perspective is going to be thinking about what's the right regulatory approach for these types of assets, given their lower emissions profile. They tend not to take a one size fits all approach, but more of a tailored approach to ensure the right regulatory regime. So I think those are the three buckets of outcomes that we're looking for in this program.
Now, if we could talk about that market dynamics aspect and kind of where a first stage project, commercial deployment of small scale goes from here. We're in an interesting policy moment in the US, particularly for hydrogen, where the 45V production tax credit has now more restrictive requirements. You need to begin construction before 2028. We have a new administration. Federal climate policy is uncertain, but states like New York still have their own requirements, as you mentioned, Will. How is this environment affecting the market for linear generators? Does policy uncertainty make this fuel flexibility advantage more valuable?
We provide lower cost and higher reliability solutions to our customers that are also higher, have higher sustainability. And so our customers care about all three things. And so the policy environment hasn't really changed our customers' buying habits or needs. And because we provide lower cost, higher reliability, and higher sustainability, we've generally been supported by by many administrations over the course of the company's history. And so we just continue to kind of keep trying to get power faster to our customers, and that's universally liked, I would say, and supported.
In a changing policy environment, flexibility is helpful. I think there, as Shannon was saying, there's benefits from this type of technology, really kind of regardless of of your particular views or what the administration's views might be, and so that does help. And then again, there's the modularity aspect and less exposure to geopolitical or macro factors that large scale infrastructure projects are exposed to.
Will, from national, given that this is the first commercial project for a hydrogen powered linear generator, do you see a future in which the deployment of linear generators is limited because the hydrogen industry isn't being deployed as quickly as was once forecasted several years ago, particularly in the US?
I don't think that's limited to linear generators, but I would say the amount of hydrogen will dictate how much is used as a fuel for power generation and in other applications. Round numbers, the amount of hydrogen that's produced in the United States today isn't even enough to power a 500 megawatt facility. So, we have a long way to go before hydrogen, can displace a material amount of the the fuel consumed, whether it's in power generation or in general. But again, that's the linear generator. One of the very attractive things about it is that ability to kind of evolve as that evolves over time.
And I guess, Shannon, with that in mind, is Mainspring Energy also looking abroad, or are your operations mainly in the US?
We're focused. We've deployed in the U.S. so far, but we are absolutely looking internationally, and we have seen a strong interest in different fuels in different countries, and that's largely again based on the availability of different resources, because certain locations have a lot of renewables, certain locations don't, and depending on what you have access to, it can be that flexibility becomes even more valuable.
Okay, and I guess, Shannon, looking 3 to 5 years out, what does realistic deployment look like for the linear generators? You said you're able to scale up manufacturing very quickly, but where are you seeing the most traction, especially these days, between utilities, data centers, industrial customers? Are we talking about gigawatts of capacity or more targeted applications?
We're really seeing strong demand across all three verticals that we work with. So industrial and enterprise customers, data centers, and utilities. And they're all trying to solve the same problem. They can't get power fast enough. Power, low cost, clean, dispatchable, reliable power is the thing that they need to scale their businesses. And because of the AI boom and because of electrification needs, it's really driven the need for power much more significantly than anyone had anticipated in the past, and it's created this very strong need. And so we see ourselves growing in all three of those areas, and we're seeing demand in all three of those areas to continue to scale. Business is booming.
Yeah. And I guess, Will, for National Grid Ventures, given this huge amount of unprecedented electricity demand that we've seen, and this initial project that you have with linear generators, we've talked about some of the success factors of the smaller project, but are you looking at additional deployments when you think about 3 to 5 years down the road? Where do you see linear generators fitting into a generation portfolio that's going to be serving data centers potentially?
For us, a couple of places. So certainly on Long Island, in and amongst our existing generation fleet. Long Island isn't seeing the same load growth as Loudoun County, Virginia, but there is load growth nonetheless, and as well as an aging generation fleet. So we're certainly looking at linear generators as a tool in our toolbox to be able to continue to provide reliable and efficient, affordable electric supply to Long Island. And then more broadly, as we think about serving large load customers, data centers in particular, it's again a great tool in the toolbox. Whether it's on its own, whether it's part of a bridge power type of approach, whether it's part of backup, whether it's mixed with other types of generation technologies and renewables to provide a kind of a blended type of power portfolio. We see lots of applications for this type of technology.
And so I guess maybe one last question for you both as we wrap up here. What do you want people to understand about this Long Island project or about linear generators more broadly? What is it that you want the general public, the listeners of the Interchange Recharged, to understand about the future of linear generators?
From the Long Island project, the perspective of the Long Island project, we'd love for folks to see that we're taking steps to look at new and innovative technologies that can solve the challenges that we have in that particular part of the New York energy system. We think there's a lot of great opportunity and significant benefits from applying linear generators, Mainspring's linear generators in this case.
Our goal is really just to get broader visibility to the technology and the value proposition that it can support lower costs, higher efficiency, lower emissions, and fuel flexibility, along with that modular and scalable build out. And we're excited to be supporting data centers and utilities with this growth in front of us.
Excellent. Shannon and Will, this has been really helpful for understanding the linear generator technology, what you're hoping to test for the Long Island project, and what success looks like. So thank you both for coming on the show and talking us through it.
It's been a pleasure.
Yeah, thank you so much for having us.
Audience, thank you for listening as always. Feel free to follow along the Interchange Recharged wherever you get your podcasts.